I'm really looking forward to showing off some of the fantastic work that's being done in the hazard modeling in the hub, and showing how a lot of it really focuses on the particular challenge that we're addressing in the hub. So lots of people model hazards, but they don't link so tightly to the hub mission, the mission to reduce disaster risk for the poor in tomorrow's cities. So there's a whole lot of different ways you can model flooding. Here we're focusing on those aspects that are most important for urban planning, for future urban planning. Earthquakes, for example, or landslides. There's lots of ways in which you can approach these things, and they're very useful, these different ways, for different problems. Here we're going to focus clearly on the ones that are most relevant to the challenges we're dealing with. Remember, this is what it's about. By 2050, this is UN Habitat's modeling. Cities in the developing world will absorb more than 2 billion new residents. 90% of the world's urban growth is going to be in the developing world, and it's an absolutely global scale challenge. It's the scale of this that makes the hub what it is. The rest, we're going to enhance that urban development through risk-informed planning and decision-making. You'll see, keep thinking of, as the speakers talk today, how that, and the speakers will focus on how their work is going to help this problem, and how we can understand the consequences of decisions we make today on the risk for tomorrow. Really important. I'll not go through the rest of this. So I'm going to hand over to Mano, who will take over. Oh, Karim, I think Karim's going to do a brief introduction to the specific talk. So over to you, Karim.
Carmina first.
Carmina.
Oh, sorry. Karim and Carmina. I'm getting those mixed up today for some reason. Sorry.
No worries. I'll share my screen. Oops. Can you all see? Oops.
Yep.
Oops. Great. Yeah, quick introduction to today's talks, particularly within the perspective of the risk working group, so how they are placed within the overall risk working group. I'm showing the same slide that I had last 2 weeks ago in the previous workshop. So where we are, pretty much a year ago, there was the establishment of the risk working group by the Hub Executive Committee. Was a smaller group of researchers from the 4 cities, from the UK, and from across disciplines, and people also from the advisory board that were essentially starting from a reflection and review of the existing way in which risk modeling works, with the idea of identify challenges, but also opportunities for our work within the tomorrow cities. So this first part, if you remember, ended pretty much soon before Christmas with the where there was the risk concept node. And then the idea was soon after Christmas to start this transition phase between the inception phase of the overall project and the actual research, strategic research part. But then we were all hit by the ODA cuts in end of March, beginning of April, so soon before Easter. And so as part of that, there was as you all know, because of the reduction in budget and resources, we had to refocus a bit the work. And so this transition phase that was planned to happen slowly right now actually was accelerated and happened pretty much between April and May. And so there was this new risk working group that is much broader than the previous one. Pretty much everybody now that is involved in the hub is part of the risk working group. And within the risk working group, there is also an early career risk working group, which is actually leading the exciting part of the research and with feedback from the senior academics and senior researchers and partners that are part of the project. So there is a lot of work in progress going on. And again, there is a formal and I know Elian is here. Elian, there is the terms of references that we've been working together for putting together in a formal way what are the aim and objective of this group, the work plan. And again, I'm not going into details of this because I think we have discussed those already in the last meeting that was specifically focused on the risk working group. But really the idea is to start with the virtual test bed, which is what we call the Tomorrowville virtual test bed, which is a fully integrated decision support environment of interacting physical and social infrastructure systems. And then the idea is to learning from this virtual test bed to actually apply some of those methodologies, some of those approaches in the real world in Kathmandu and Nairobi. And then there will be a final part toward the end of the financial year, so in soon after Christmas, pretty much, where we already had started this part, but the idea is to interact more and more with Global Facility for Disaster Risk and Recovery at World Bank, the United UNDRR, Center for Disaster Protection in the UK, and so on. So global partners that will help facilitating the scaling up of our approach to ideally any other city that is interested in applying this. And as I said, in the very first part of this risk working group 1 year ago, we started with this review reflection phase. Again, I think you have seen this so many times that everybody knows well what are the limitations of current approaches, but today I'm highlighting those that are relevant for today's meeting. So particularly when we look at hazard modeling, there is a lot of reliance on empirical data and some assumptions that are physically unsound. And this heavy reliance on empirical data, particularly in data scarce region, is definitely a problem. So what we are trying to do is to promote the use of physics-based type of hazard modeling approaches to overcome those limitations. So we again, you are all familiar by now with the conceptual framework that we have developed as part of the risk concept and the various iterations that you have seen in the past meeting, where we are making this now operationally in real life. And remember, I think I like to stress, and something that is important is not just another risk model, another modeling framework is really a purely computational tool implementing this model. It's really an environment where the engagement with stakeholders, the co-production, the participatory approach really will play a key role. So it's not really, again, the engine, that this gray box that you see here, which is the modeling part, the more technical modeling part, but it's really the entire framework that also include for instance, the decision fora, which is really possibly the most important part of the overall process. So again, it's the possible state of the art and best high quality and best research ever. Of course, there will be coding, visualization tools, and software implementing some of those models and methods. But really, then the key part is really all this co-production with stakeholders, with researchers, to make sure that we have a risk-informed decision environment for tomorrow cities. And so today's talk is really in this first is a fairly small, it's a small part of the overall framework, but it's very important because it's really the input is one of the key input in to make sure that then the entire process will work. And again, I'm not going into details of all the blocks, is the feedback loops, and you have seen this so many times, and by now I assume everybody has been reading some of the documents that we have produced, that I don't think there is really need to go in detail. But so the focus today is on this multi-hazard simulation, which is the input for the scenario consequences impact assessment that in turn are the input for the decision for the overall feedback loop that will inform our decision making. Within this hazard modeling, today you'll hear first from Karim, that will talk about seismic hazard modeling, and then Manu will show some of the methodology used for flood hazard modeling, followed by Luke on landslide, and then Maggie will show how some of those methodologies presented by Karim, Manu, and Luke are being implemented in the virtual test bed of Tomorrowville. And then we'll have 30-40 minutes at the end for Q&A. Thank you. Karim, stage is yours.
Thanks, Carmine. I guess you guys can see my screen now.
Yes, we can.
Thank you. So I'll talk about the physics-based earthquake ground motion simulation, from about methodologies, challenges, and utilization of them. So if we go to the basics, what we need to know about earthquakes is that where they happen and how large they will be. This is usually dealt with utilizing earthquake source model or rupture forecast models. The second major component of quantifying seismic hazard is to utilize a ground motion model. The conventional approach is to utilize empirical ground motion model, shown here as approach one, and the second approach is to use simulation. There is a range of simulations we can utilize. Some of them more rigorously honor the physics of the phenomena. So if we talk about the conventional approach and try to see why we want to move away from this, if we have a look into the empirical recorded ground motion data set, this is the plot that shows the magnitude of the events versus the distance from the source of the event. And the important part of this plot is this red box here, which is large magnitude events close to the fault that we don't have much recordings about for them. For example, for below magnitude 5, we have lots of recordings. Usually for engineered structures, they are not of concern. But for this critical area, we usually do not have recorded ground motion. Specifically, if you want to talk about region-specific seismic hazard analysis, you will have a major challenge. You need to utilize models or ground motions from different regions. In the empirical modeling, we take these blue points and then we try to fit a model through that using a statistical approach, a model that is fitted to a given magnitude, and also it varies with the distance from the source of the earthquake. What you see is that this solid line represents the median of the ground shaking, and this band represents the uncertainty. The assumption in the empirical approach is that any differences that you see in the amplitude of the shaking, it's a stochastic phenomenon, and you lump everything together and you end up with this wide band for the uncertainty. Let's have a look at the application of this type of modeling so that you can use for loss assessment, but let's see what are the problems here. So if you use empirical approach and this is your fault, this is the epicenter of the fault, what you see is that the ground shaking attenuates as you go away from the fault. None of these variations are basically honoring details of the Earth's surface and the deeper crust. As you can see, this attenuation is actually coming from this attenuation shown in this figure. So in the past few decades, there has been developments in the empirical ground motion modeling. So there are many versions of these types of modelings have been proposed. What we see is that the uncertainty, this band that is given by this empirical ground motion model hasn't decreased. And this is, you need to consider the fact that the amount of data has increased many times, and also the complexity of them has increased. So the ground motion models in the 70s, they were one line of equation. Ground motion in 2020 are 3 pages of equations. Regardless of this, let's say, development, we haven't seen decrease in the uncertainty of the ground motion estimates. So what is the problem is basically the simplified approach that is used in empirical approach, which overlooks the physics of the phenomenon. For example, for the earthquake source, you only use magnitude of the earthquakes, but we know that even for a given site, 2 magnitude 6 events at the same distance will produce different levels of ground shake because of the characteristics of the source. So here's the conventional modeling. So what is the solution for this type of approaches? One of the solutions is to use physics-based ground motion simulation. In this approach, the underlying physical properties of the Earth is honored in the modeling. They are explicitly put into the simulation framework and the code, and the 3D and different aspects of the source is also represented. What you see here in this figure is that the different parts of the of a given fold is displaced with different amplitudes and in different directions, and the arrival of the rupture for different locations of the fold is different. So by incorporating these types of physical actual properties of the earthquakes and solving the governing equation of the motion for every point on in the earth in the model that you have considered, you will be able to represent the physics of the hazard. So I will go, how much difference do we see when we utilize this type of approach? This is the same figure from the previous slide that I showed. The attenuation, the uniform attenuation of the ground shaking as you go far away from the source. This, on the right-hand side, is the simulation for the same event. And the simulation results are significantly different. This is because the underlying properties of the earth and also source rupture, the earthquake rupture, is considered in the simulation. As you can see, for high slip areas close to the fold, you see higher amplitudes. The underlying basin structure in this region results in the amplification of the ground shaking, as you can see here. Also, the channeling of the energy of the earthquake towards softer areas results in higher amplitudes here. This is significantly different in terms of the damage that you will observe in the structure and the type of loss that you estimate and the risk measures and the policies you will implement towards mitigation of the consequences of this, or when you plan your urban development. So here's an application of this type of approach for Kathmandu, where, for example, in this application, the 3D basin structure of the Kathmandu is considered in the model. The source is put under the Kathmandu basin along the main Himalayan fault, and these are the properties of the source in terms of the displacement and the arrival of the rupture on the fault and the amount of energy that is released. What is important here is that for this example that I'm showing, I have utilized a very simplified 1D profile for the properties of the basin and another 1D profile for the properties of the deeper cross. We know that the earth is not as simple as 1D profile. This is one of the major challenges. In order to be able to represent the reality and come up with results that we can rely on for urban development, we need to basically move away from this 1D modeling towards more accurate modeling of the earth. And I will mention two types of work that Tomorrow Cities is doing in that regard. This is one of them. Ravi Panjani from Tribhuvan University is working on under the supervision from me and from other professors to try to extract data from the existing published models and also existing published source inversions of the other publication, and build a velocity model that is reflecting the quote-unquote reality. This is something that we will progressively implement in our next generation of simulations. The other types of work that is being done is to conduct passive seismology. After the monsoon season, this will be started, and by getting data from this approach, we will be able to conduct inversion to understand the properties of this and supplement that with this type of modeling. So what do we get at the end is this type of ground shaking modeling. And the important thing that I want to highlight, that this model is a 3D model of the rupture, and the velocity profiles are only 1D in the basin and 1D in the out of the basin. However, you would be able to see the progression of the seismic waves. And two important properties to note is highlighted here. The ground shaking in the basin is large in terms of the amplitude as shown here, whereas in the outcrop is not. And the other part is that you see the pulse-like motion of the soft sediment and also reverberation towards the end. This type of approach, even with limited data, is able to represent this, the reality, quote unquote reality of the earthquake ground motion phenomena. And our approach is to utilize this rigorous physics-based modeling in our quantification of the hazard. One aspect, important aspect, is to make sure that the models we are using and the type of approach we are using for simulation is sensible and is validated. This is the one, I will say, initial phase of validation that has been conducted based on the Gorka simulation, where the simulation results shown here in terms of the vertical displacement is in the close to the hypocenter is kind of consistent with the actual observations that has been obtained from the INSAR and GPS. Obviously, there are differences, and those differences will be revised as we get more data, and based on the validation that we will conduct, we will be able to revise and make our models better and better to represent the reality. This will enable us to use those models to conduct simulation that can be used in the urban developments. So I will quickly mention this, but Maggie will discuss deeply about this. Here's an application. You saw the application of physics-based for New Zealand and for Kathmandu in a larger scale area. For tomorrow, well, even for a very small scale region, we were able to honor the physics. So quickly, you have these low income areas here where poor people will live. And those areas will be filled with softer sediments. If you conduct a simulation based on a realization of magnitude 6, you will end up with high levels of ground shaking here. So this is the core of the Tomorrowville's approach to rigorously represent the physics in order to be able to honor what is real, which will hit the poor and other demographics of the society. If you were to use empirical modeling, you wouldn't be able to distinguish between a point here and a point here. Another strand of the work that is being done is to understand the seismic tectonics of the Kathmandu. This is the work that is led by Himanshu Agrawal from University of Edinburgh. I wouldn't explain these. He's doing a great job in describing in understanding what properties are affecting the source realization and how we can use them in a sensible, generating sensible scenarios for Kathmandu region. He's also developing a workflow for streamlined end-to-end simulation that will enable us to streamline the whole process of the simulation from his side. The important point here in terms of utilization is that in order to be able to distinguish between, in order to be able to have inputs that are usable for different parts of a community, the physics of the hazard should also be able to represent the hazard modeling should be able to represent the physics. In the ground motion simulation approach that I presented, the high frequency and low frequency range of the ground shakings are properly represented, which will enable us to utilize them both for quantifying the loss for low rise building and for high rise building. This will also be tied with the velocity modeling, validation, and source modeling. Because of the time constraint, I wouldn't be able to explain further. At the end, the challenges will be to, there are a list of technical and non-technical challenges. A few of them would be to gather the data, existing data for the earthquakes that are recorded in the Kathmandu region and try to validate the models based on those, which will enable us to deliver high quality hazard models and outputs. The other one would be the work around the passive seismology. By getting the data through the passive seismology, we would be able to directly utilize the data in terms of in order to inform the simulation. This will put us in a cutting edge of this type of research by direct utilization of the inversion results from passive seismology towards forward simulation. High performance computing is also another challenge that we are dealing with, but that's quite manageable at the moment. There are large list of work that is being done. I don't know if I'm over time, but I will leave this here, or maybe I can discuss them through your comments. That we are doing documentation of the velocity modeling work now, and also preparation for the validation of based on small magnitude rupture and scenario selection. Okay.